Hello AP, Chapter 8. It's a new day, a new topic. In this chapter, you're going to learn not only 3 types of bonds, but you're going to learn how to draw molecules and compounds. We are going to do our drawing skills and show me those fabulous skills. We're going to start with 8.1, so get those periodic tables, get those pencils ready, or your highlighters or color pencils. And also, don't want to get you too excited, but in this chapter, guess what's coming back? We got math. We got math. We're going to use a calculator. Unfortunately, not till the end. So you got a couple sections first. So 8.1, we have a new learning objectives. We're now going to start to hit the learning objectives on AP Classroom Unit 2. So we should, with this chapter plus Chapter 9, get through all of the 7 learning objectives that are in these Unit 2s. So the first one right here, 3.A. Explain the relationship between the type of bonding and the properties of the elements that are in those bonds. Okay, so there are 3 types of bonds right here. 3 types. Now you know of 2 of them, okay, but we never got to talk too much about metallic bonding. So in this learning objective, you have to know a thing called electronegativity. And you're going to see this guy pop up about the middle of the chapter. He is one of the 4 trends that you have to know. Okay, now remember the 4 trends? We talked about ionic radius, atomic radius. We talked about ionization energy, electron affinity, and here comes Mr. Electronegativity. You saw his name pop up a little bit in Chapter 7, but I told you I wasn't going to discuss it in Chapter 8 until Chapter 8. So the difference in electronegativity is not the only factor in determining if a bond should be designated as ionic or covalent. Okay? Generally, bonds between a metal and a nonmetal are ionic, and bonds between 2 nonmetals are covalent. And we know that. We've been doing that for 2 years. The other word for covalent, we like to sometimes use molecular because they're molecules. Okay? Examination of the properties of a compound is the best way to characterize the type of bonding, which means we're looking at those properties big time. So compounds versus molecules. And we have what's called ionic compounds, and we have molecular molecules or covalent. So this word molecules, you may use either molecular bonding or covalent. Okay, either one is the same thing. The likelihood that 2 elements will form a chemical bond is determined by the interaction between the valence electrons and the nucleus. And remember that nucleus, Mr. Protons. Mr. Protons doing a lot of help also. Valence electrons are responsible for any time we have a chemical reaction. They are the hardest working electrons. Okay, remember the core are protecting the nucleus, but the valence electrons are losing and gaining to form whatever compounds or molecules or bonds that they're trying to form. When 2 atoms or ions are strongly attracted to one another, then we can form a chemical bond. Okay? In a chemical bond, electrons are either shared, and this is where covalent is coming in, or lost and gained, called ionic, between the atoms. So the 3 types of bonding, you can have ionic bonds, which we know, metals and nonmetals, but more specifically, its true definition is the forces that hold those ions together. So when sodium loses that 1 electron and chlorine gains that 1 electron, then you'll have what's called electrostatic forces that attract these 2 together to form that bond. So right in between here, we draw a dash to indicate that that is a bond. And because it's between a metal and a nonmetal, we call it an ionic bond. Okay, so this little dash right here, what you're seeing in there, it's the 2 electrons that are between those 2 atoms. Okay, well actually they're ions. So the 2 electrons that are being held together between the sodium and the chlorine. Sorry, I'm getting these messages. Hold on. All right, sorry about that. Sodium and chlorine, so those two electrons right there, sodium gave the electron up to chlorine, and chlorine now has his octet. And that little dash line right there, that represents 2 electrons. Covalent bonds are the sharing of those electrons between the atoms. There's no losing gain, no charges. So no charges, which means no lost or gained. Okay? They're sharing them. So what happens is when you have somebody like CO2, okay, or diatomic, I'll do diatomic chlorine. Okay, there's also a bond. But this bond right here, because it's nonmetal bonded with nonmetal, it's a covalent bond. And there's still 2 electrons inside that bond, but they are sharing those electrons. It's not a give and take. They are sharing the electrons. But the question is it equal sharing? Okay, so is it equal or is it not equal? Metallic bonds have to do with metals nuclei floating in a sea of electrons. So you will literally only see the metals, or you would see what's called like alloys. In alloys, they are a blend of metals. So like the greatest examples of alloys would be like coins, jewelry, steel. So coins, jewelry, or steel, those would be like metals blending, notice I didn't say bonding, blending with other metals, okay? So any type of metal and their nuclei floating in a sea of electrons. As I told you, we're going to get more into this guy, chapter 11 and 12, okay? This chapter, I'm going to be focusing more on these two, and chapter 9 also. So this right here, you're going to see in chapter 8 and 9, okay? So metals and nonmetals, we already know where metals and nonmetals are. Nonmetals and nonmetals, covalent bonding, okay? Now we got Lewis structures, okay? Valence electrons, we already know valence electrons, those outer shell of electrons, okay, the hardest working electrons. So in these valence electrons, what usually happens is you have an incomplete orbital, which means you're missing electrons. And we already know how to figure out how many valence just by looking at the periodic table. If you do not have your periodic table labeled, please do. Everybody in group 1 has 1 valence, group 2 has 2. These guys, for valence, the D block, most have 2 valence electrons, but there are some that have 1, and it's these special groups, okay? These special groups have 1 valence electrons, okay? And you know when you do the electron configuration. So most of the D block and the Fs, they have 2 valence electrons because of the S orbital that's right before it, okay, before the Ds. And if I jump over here to borons, I go 3, 4, 5, 6, 7, and then I got 8. So remember these valence electrons, it's the A groups, okay, the representative groups. That is kind of like a cheat way of trying to figure out which of the valence electrons you have without doing electron configuration. Now be very careful with this number 8. I mean number 8 headed down. Mr. Helium, he only has 2. Because he only has 2 electrons. How can he have 8 valence electrons if he doesn't even have more than 2? Come on, it doesn't even make any sense. Okay, but you knew that. You knew that. So what we do is we represent Lewis structures. We represent electrons by this thing called dots, called Lewis symbols, after a scientist named Mr. Lewis. Okay, you'll hear his name pop up again. As a picture understanding, a pictorial understanding of where the electrons are in the atom, we represent electrons with dots. Okay? And how you put these dots around the symbols of the electrons, I'm sorry, the symbols of the elements does matter. So whatever valence electrons they have, you use dots. Okay, so it's kind of like orbital diagrams with the boxes and the arrows, but it's kind of a shorter version. So if I was going to do Mr. Hydrogen, hydrogen has one valence electron, so I would put one dot. Okay. Beryllium has two valence electrons. Okay. Now, there is a rhyme or reason on where you put the dots. Okay. So remember there was a scientist called Mr. Hund, okay, back in chapter 7. And remember he had this thing called like the school bus rule? Well, that's what I called it, the school bus rule. Where you had to fill an electron in an orbital first with the same spin before you doubled up with that opposite spin. Okay? So what happens is it's like the symbols too. If beryllium has two valence electrons, I can't double up on the dot. So what I'm going to do is put my second dot, I'm going to put it on top. Could you put it on the bottom? Yes. Okay. Could you put it on the other side? Yes. Okay. You just can't double it up. So when you're doing these symbols, it's like a north, south, east, west, up, down, left, or right. Okay. I'm going to jump over here to boron. Boron has three valence electrons, so I'm going to put a dot on each side. Okay, 1, 2, 3. And I got carbon, that's got 4. And you can even do Lewis symbols with the transitions too. Only group A has one electron on each side of that symbol. Now, as soon as you get to right here, once you get to number 5, then you start to double up. Okay, so right here, nitrogen, if I go 1, 2, 3, 4, then I'm going to double up. And I usually like to double up where I left off. And you put it right next to it, like a little colon. Okay. And over here, oxygen. So I'm going to go 1, 2, 3, 4. Now oxygen has 6 valence electrons, so I'm going to double up right here. And then I'm going to double up right there. Okay, so like I said, like a colon. And then fluorine has 7. So we're going to put 1 on each side. But then I'm going to double up, double, and then double. Okay, so now once we get to neon, that has all 8 of them, you should have 8 valence electrons representing as dots around that symbol. Okay, so we kind of have like what's called a generic symbol, where I like to put them in certain orders because it makes sense in this order, and then that's why I'm going to show you this order. I start my dots on the right side, and then I go around counterclockwise. So 1, 2, 3, 4. So I go around counterclockwise, and then I put my 5th dot right next to it, and then 6, 7, 8. So I start and I end in the same position. Okay, so you go counterclockwise and then clockwise. Does it matter where you start? No, it doesn't. Okay, but it does make sense why I start over here when I get to 8.2, the drawings. Okay, so these are called Lewis dot structures. Okay, and it's to represent the dots equal electrons. Okay, so the number of valence electrons available for bonding are unpaired dots. Okay, so see how these lonely dots right here? That means that they are available to bond with another element. Okay, but when you have these paired dots, they're not too much available for bonding. Now they can, but they are not too much available. So we're going to get to those rules when we get to the drawings. The octet rule, we know that magic number is 8. That's what octet means. The octet rule means that any atom will gain, lose, share whatever electrons they want to be surrounded by those 8 valence electrons. Okay, so lose, gain, do whatever it needs to do to get to the magic 8. Now there are some exceptions to the rule. Hydrogen and helium will only ever get to 2. That's it. That's all they can do. There are some other exceptions also in group 3A, which is right here, boron's group. They tend to the most get to 6. And you'll know why, like I said, when we get to the drawings. So anybody in group A, right here 3A, So boron, aluminum, gallium, so forth, they don't tend to get to 8. The most they can usually do is 6 because 3 times 2 is 6. The octet are the ones that occupy all of the s and p's orbitals because valence electrons only involve s's and p's. So the most noble gas configuration you can ever get is an S2P6. And we call this energetically favored. We never say the word stable. Okay? Energetically favorable, that means this is a configuration that has the lowest possible energy for an atom. We assume that an atom is favorable when surrounded by those 8 electrons, okay? Which basically means in your symbol, if every bond is 2 electrons, then we want to see 4 bonds. 8 electrons, 4 electron pairs, which an electron pair is called a chemical bond. Okay? Now, whether that bond's ionic or covalent just depends on who the elements are. So Lewis dot structures, I just abbreviated in my notes, LDS, Lewis dot structures for atoms. Simply ignore a square around, simply imagine a square around the element symbol, and then you place the valence electrons around the symbol. Remember Hund's rule, right there, Mr. Hund. Put 1 electron around each symbol, and then you go and double up, okay? Be very careful with symbols with charges, okay? So determine how many valence electrons the ion will have if it gains or loses. So most metals, we know the metals, they want to lose, and nonmetals want to gain. Okay, it's a fact of life. It'll always happen. So the metals will lose, and most of the time they're going to lose their s orbitals first. Then they'll lose some p's. Okay, and the reason why p's is because this side, the p's, this is more near the staircase. So those elements near that staircase, near element staircase, they're the ones that actually lose the p's first. But the majority of the metals lose the s's first. Nonmetals will gain enough electrons to fill their p orbital. Okay, so I'm going to highlight both. So what you do is this. Okay, so say you have sodium. Sodium has 1 valence electron, so he's got 1 dot. Let's say sodium lost an electron. Okay, so what you do is you lost that electron. That means that guy, you lost him. So if you lose that 1 electron, you're out of dots. So what you do is you put the whole symbol in brackets, right there, in brackets, and then you put the charge as a superscript, aka an exponent, in the upper right corner to show that that element lost an electron. Okay? So if you lost 2, 3, whatever it may be, you put the element in brackets and you put the charge in the corner. What if he gains? Okay, let's say it's chlorine. Chlorine has 7 valence electrons, so we put 7 dots. Okay, and we know chlorine's a nonmetal. He's going to gain an electron. So what if he gained 1 electron? Well, he's going to gain it, and now he's going to be a complete octet. So he went from 7 electrons now to 8. But you have to show me that he gained. So we put them in brackets with the negative on the outside. So remember I told you AP wants to see brackets. We usually never use parentheses unless we're doing math. Okay, so brackets for symbols, brackets for chemistry terms, but no parentheses. Okay, now this is where the confusion happens with students regarding valence electrons. Sodium went from 1 valence electron to 0. No, he's got valence. But now, what does his configuration look like? Well, his configuration looks like neon. Okay? So, neon's configuration, it's got 8 valence electrons. So, regardless, and I'm going to bring my good friend Joel into this. Yes, Joel, I don't forget. Every element has valence. Regardless if they lose or gain, Every element has valence. So if it loses, make sure you understand what his electron configuration now looks like. And his configuration looks like neon, which neon has 8 valence electrons. Chlorine went from 7 and gained 1. Okay, now he has 8 valence electrons. Easy enough. Okay. Let's practice a little bit of symbols. Write the Lewis symbol. This is when we need Mr. Periodic Table. Write the symbols for each of the following and the dots. Okay. So aluminum is in group 3A. So he's got 3 valence electrons. 1, 2, and 3. Bromine is in group 7A. So he's got 7 valence electrons. Okay. Argon, noble gas, in group 8A, so he's got 8 valence electrons, and he's completely filled with this octet. Okay. And then you have strontium, which I believe strontium's in group 2A, and he's got 2 valence electrons. Okay. Easy peasy. All right. Pretty simple enough. And if we have a couple charges, okay, let's do the same thing for potassium. Potassium's in group 1, so he's got 1 valence electron. And if I had arsenic, and arsenic's over there in 5A, so he's got 5 valence electrons. And I'm going to double up right down there at the bottom. And now we got 10. Okay, now the element 10 is in 4A. Okay, he's sitting right there under germanium. But then he goes and loses 2 electrons. And I don't want it to make it look like I'm doing a chemical reaction. He loses 2 electrons and becomes 10 plus 2. Well, if he had 4 electrons, 4 valence electrons, and he lost 2, well, he still has 2 left. Okay, so it doesn't mean the dots disappear. He still has 2 left. But I do have to put that in brackets with the plus 2 on the outside. Okay, if we would have lost all 4, then his dots are gone. He still has valence. It just now looks like a noble gas configuration. And if you gain, last one, Mr. Nitrogen. Nitrogen's in group 5A. 4, 5. And now, if he gains -3, means he gains 3 electrons. Well, I'm just going to complete his octet. So 1, 2, 3, 4, 5, and then now 6, 7, 8. Because he gained, I have to show that he gained 3 electrons. Okay? I want to make this one last point with the dots. Okay? The correct dots look like colons on the outside, okay, and the 2 kind of periods kind of right next to each other. I have seen this before, and I don't know where anybody has ever been taught something like this, but we do not, ladies and gentlemen, ever do a star type of pattern with the dots, okay? Don't be that child. Don't do that, okay? And if you find whoever does that, let me know, because they're doing it wrong, okay? Make the dots look like they're on top of each other or next to each other, okay? Something like that. So like colons or kind of